There we go. Awesome. Hopefully you can see my title screen. Yep. All good? Okay, awesome. Well, so thanks for coming along and having a listen. Not that you had to go very far for some of you. But I'm Clara Barker. I'm a material scientist at Oxford University, and I'm also the chair of the LGBT plus advisory group at Oxford University and involved in various LGBT things. So hopefully my screen works. Yes. So I'm going to start with the basics. What is material science? Oh, we've got a hand wave.
Can you accept my friend Freddie into the call, please?
Ah.
He wants to be here. I'll mute myself now.
Yeah, what is material science? Because not everyone actually knows what it is. So material science, if we take a little bit of chemistry, a little bit of engineering, a little bit of physics, and we smoosh it all up, it's basically a hybrid of different disciplines in science. And so what I found is that throughout my career, I've been in chemistry departments, engineering departments, but at Oxford, we've actually got a materials department, which is quite nice. So an entire department dedicated to materials, which is fantastic. And what is it that we want to do? Basically, if we take something like a carbon atom, something really basic like a carbon atom, what we know is that depending on how we arrange the atoms of the carbon, then we can get different material properties. So graphite is very soft and it's very dark. Diamond is transparent and glassy. Fullerene has different properties. So depending on the structure, then we change the properties of the film. And so that's exactly what we want to do, really. We want to play around with that structure, even though we've got the same Lego brick starting point, and see if we can change the properties of our films. And thin films, I work in materials, but I specialize in thin films. So for me, that's somewhere between a monolayer and several micrometers. If we think that the human hair is around 70 micrometers, to me, that's a mountain. That's huge. I want nothing to do with that. I want to keep it thin. And we can use different techniques to put down our thin film. So there's electroplating and printing. I've used chemical vapor deposition quite a lot. But actually what I'm going to talk about for the first part of this talk is various physical vapor deposition techniques. So I'm going to go into a few of those different techniques. And what do we actually make? Well, if we take some cheap sunglasses, hopefully they've got UV blocking on them. So they've got a thin layer of material that blocks UV from getting in. If we take our more expensive optical glasses, then maybe we've got anti-scratch coatings, maybe anti-reflective coatings, something along those lines. We've got different thin layers on top of the glass in order to give us functionality. And solar cells, photocatalytic cells, they made up of various thin films. Mobile phone touchscreens, so the touchscreen technology is actually a series of different layers, thin films, although they don't stop you from breaking your phone if you are me in this case. And you can even do other things. So one of the projects I worked on, we took a material called PEEK and we coated that with titanium layers to make them biocompatible. And these were actually for spinal implants. So not that this particular one was getting put in someone's body, but hopefully, you know, it's a prototype for ones that will be, which is kind of a bit weird and cool. So we've got different ways of making these films, and we won't necessarily choose one. There could be different ways of doing it. I'm going to go through a few of these different thin film deposition techniques. So generally we start out with a metal box. This is our chamber, and it's big. Yeah, basically it's a big metal box which is vacuum tight, and we have a substrate inside there. So this is the material that we're going to make our thin film on, that we're going to grow our thin film on. So if we're making thin layers for our glasses, these will be the glass lenses that we put in. That will be our substrate. And then we, so the first example I'm going to do is evaporation. So my career in material science, I started out doing an electrical engineering degree, and then I ended up working for a company that made machines that did evaporation. And so this is how I got into it. In fact, they made machines that put the metal on the inside of crisp packets to keep your crisps fresh. So how do we do this? Well, we take a ceramic crucible and we fill it with our base material. So this could be a powder, it could be chunks of metal. Like I say, we're starting off with, for example, aluminium, and we're going to make a thin film of aluminium. However, it's the structure that we're changing. We're not trying to change aluminium into titanium or something like that. We're just trying to change the structure. And then we suck all the air out, so it's under vacuum. And we heat up the crucible until it gets nice and hot. And at a certain point, the material is going to melt, and then it's going to start evaporating. And so the material is going to evaporate, and it's going to coalesce on our substrate. And it's going to grow bit by bit, and hopefully we'll make a thin film. And a similar sort of process is another evaporation system. However, this time we've got rather than a crucible, we've got a resistive boat, which we heat up, and then we can have a feed of wire. So looking industrially, this is the sort of thing that I used to do for the company. You can feed the wire in continuously, and it will melt and drip onto the surface and then evaporate. We can also put a mask in front of it. So not only do we have material landing on the substrate, but if we put a mask there, we can actually make up different circuits. We can actually choose where that material lands, and so we can make patterns basically. And so similar sort of thing, the material evaporates, and some of it will land on the substrate, but some of it will land on the mask, which is really cool. So that then when we remove the mask, what we see is we're left with this patterned material behind, so this patterned thin film. So this is how we can make like circuit boards, something along those lines. A little bit more complicated. I'm moving on to pulse laser deposition. So we actually have two pulse laser deposition systems in my lab. We have one laser between the two of them. And we start out with the similar sort of building blocks. We've got the metal chamber, we've got our substrate, but this time instead of having a crucible or a boat, we actually have a target of the material. So this will be a chunk of the material. And this can be powder, but not necessarily. And once again, we put it under vacuum.
Oh, fuck me harder. Oh, that's it, you big studly man. Oh, yeah.
Oh, yeah. Oh.
Interesting.
My apologies.
Yeah. So we've got, this time we take a pulse, so in this case, we've got a pulsed class 4 laser, and we basically whack the target with it. We send the high pulse of the laser at the target, and hopefully this point evaporates the material, and that travels through the vacuum and coalesces on our substrate. So we can then move the target and move the substrate, or we can move the laser, and we can keep doing this. So by moving the target and the substrate, then we're moving the area that we're evaporating, and so we'll grow a thin film this way. And we can keep doing this again. And actually what we see is that it gives us this very, very intense pulse. Every time the laser hits the target, it gives off this real flash. I've got a little GIF on screen of this pulsing, although it is slowed down because it's quite a fast repetition. And what's quite nice is that by changing the frequency of the laser, by changing the energy that we supply to the laser, we can tune the structure of the thin films that we grow. And it's the same with the background pressure and the background gas and things like that. There's a lot of things that we can tune in order to change the structure of the films we make. And it's the same with evaporation. Again, we can change the temperature that we heat the material at, or we can change the background material. Now I'm going to talk a little bit about another technique, magnetron sputtering. This is my particular kind of baby. I've been working on magnetron sputtering for 15 years or so, and so this is one of those materials that processes that I always come back to. And again, we've got a metal target chamber, we've got our substrate, and we've got a target material. However, this time we put magnets behind the target. So we have an outer pole and an inner pole, and this means that above the target surface we have this magnetic field. So one pole around the outside and a different pole on the inside. And this is where we get the name magnetron from. Then we suck out the air once again, and we apply a large negative voltage to the target. And I'll talk about why we do that shortly. So in the system, we have these electrons. These electrons are bouncing around, minding their own business, but at some point they might get trapped in the magnetic field. And so when they do, they start to just bounce around the target surface. They actually travel in a corkscrew direction, and the area that they bounce around we call the racetrack. And what we can also do is introduce some argon. So we can introduce these atoms of argon and they'll bounce around the system. Obviously, these aren't to scale. I know that atoms are bigger than electrons. I'm just trying to exaggerate with my animations. And also, you know, this isn't to real time. I've kind of, you know, played with the timing a little bit here. So we've got this argon atom and it's bouncing around the chamber. And then if we're lucky, what might happen is that it might collide with the electron. When it does, it will knock off another electron. So we've got another electron in the system. And the actual atom of argon, because it's lost an electron, it becomes an argon ion, which is positively charged. It accelerates towards the negative voltage at the target. And when it hits, we have this kind of snooker or pool-like collision happening, and the atoms all bounce around in the target, and hopefully some of them will get knocked off, travel through the vacuum and coalesce, and that's the start of our thin film. And then maybe the argon ion will recombine with some with an electron. Maybe it'll get sucked out of the system, it's being actively pumped, and maybe more electrons will get trapped in the magnetic field. And so basically what we've got with magnetron sputtering is lightning in a box. It's as simple as that. And obviously we don't see the individual atoms or ions, but what we do see is kind of this nice plasma glow. And that's really cool. So depending on which materials you use, you can change the color of the plasma. So titanium target with an argon atmosphere can give you a nice blue plasma, and zinc with oxygen and argon gas can give you like a nice purpley pinky color. And so that used to be my excuse for changing the color of my hair every time I presented different plasmas at a conference. So we build up, again, we build up the thin film from all these atoms that are arriving at the substrate. And again, depending on the voltage, the current, the background pressure, all these different things give us ways of controlling the thin film that arrives at the surface. And when they arrive at the surface, if they have enough energy, they can move around a little bit. So lots of things, lots of ways to tweak the films, to tweak the structure. And I've put on screen some micrographs, some cross-section micrographs. The different parameters don't really matter, but you know, one of the images looks a bit like kind of cornflakes piled on top of each other with lots of gaps and spaces between each other. And some of the other ones look a lot harder and denser, a bit glassier. And so this is the same material, similar properties, but just changing the energy or the background pressure that we're giving to it. Of course, by eye, you can't see any different because the cross-section of these micrographs is about 1.5 micrometers. And what I did for about 10 years during my PhD and postdocs was actually I took the voltage that we were supplying to a magnetron and I ran it through a high power impulse magnetron sputtering pulsar unit. So this is inductors and capacitors. And so now what we're doing is that rather than having a DC voltage being supplied to the target, we're actually pulsing it. So we have hundreds of volts, but we can also have hundreds of amps at the same time. So this is very high power. And we have pulses of maybe 100, 200 microseconds, but then we have a long off period. This gives us a low duty cycle of around 1%. And I'll talk a little bit more about why we do that. But one of the main things that we can do with that is that not only are we knocking off atoms of the target material, but we can actually knock off ions of the target material. We're actually hitting it with enough force that we're actually ionizing this target material. So when it lands on the substrate, it's got a lot more energy. And so this is really interesting. This allows us to really tune the properties of the structure. And I said before that we can't see, we can't see the individual atoms or ions in the plasma, but actually what we can do is measure the wavelengths that are there in the chamber, and we can figure out that this one's a titanium atom peak, and this one's a titanium ion peak, and this one's an argon ion peak. So we can actually figure out what species we've got in the system. What we can also do as well with all of these techniques is we can introduce a reactive gas, so nitrogen or oxygen. So what we do is we have all this sputtered material coming off, and we populate the chamber with some reactive gas as well. And so hopefully what happens is we form compounds, we form molecules. And so now, instead of having titanium that's growing on our film, for example, if we introduce oxygen, we can grow titanium oxide. And again, by changing the properties of the energy to the system, we can change whether we have rutile or anatase or a mix of that titanium. So we're changing the structure of this material again. So we have these solar cells, and they'll look real nice. Of course, our photocatalytic cells don't necessarily look that nice in the lab. And I put on screen some examples, and two of the examples that I put on are kind of burnt, they're kind of melted. So I use these with standard magnetron sputtering, and the substrate that I used is a thin plastic piece of web. And what's happened is it's overheated, it's melted, it's deformed the plastic, which isn't great for our substrate. However, the high pins, even though we're talking maybe 100 amps and 800 volts, there's one of the examples hasn't been melted, and this actually was done with high pins. So this very low duty cycle allowed us to deposit photocatalytic titanium on the plastic substrate without melting it. And so in terms of manufacturing it, there's a lot of advantages to being able to use thin plastic web, because you can roll plastic web through the system rather than breaking vacuum to replace the substrates each time. So even though it's a much more energetic process, we did actually make photocatalytic material. So that's kind of cool. So I've given you 3 different examples of deposition techniques, and like I say, you can use them to make all sorts of thin films. For me, I'm more interested in the processes. I like the process of making the films. But some of those films I've made hardness films, photocatalytic films, transparent conductive oxides. I currently work in the Centre for Applied Superconductivity, so presumably I make superconductors. Although we do also have a lot of battery work going on as well, because making batteries is sexy and it gets you grant money. And actually the most recent thing that I made was some stainless steel films. So in the lab, we've got a couple of pulse laser deposition systems and a couple of magnetron sputtering systems, and then we've got different ways of measuring them. So like I say, you can make superconductors, you can make thin films by different techniques, and we're mostly using pulse laser deposition and magnetron sputtering in our lab at the moment. And bulk superconductors look really cool. So if you've ever seen the experiment of a cooled down superconductor, you'll see it floating above a magnetic track, something along those lines. So we can do that sort of thing. You can do the same thing with a thin film, although it doesn't look as visually impressive. So I sort of tend to show experiments using bulks, but I am very interested in the thin versions of these. And so we know how different techniques for making superconductors, but what I'll talk a little bit about what superconductivity is, because this fits in with the theme of scattering ions and ions. So we have our atoms, and they're arranged in a crystal structure that we've tuned by changing the parameters, the way we've made the film. And with standard materials, so if we look at the atoms, what we know is we've got this nucleus, and then we've got these rings of electrons that are circling around it in a very basic, very simplified manner. And if we apply a voltage to a conducting material, then what we can do is we can basically, there's one electron in the outer ring, then we can rip that off quite easily. So we can get this system of electrons passing through the crystal structure, what we used to call in high school as a sea of electrons. And this is what we use for conductivity. But this isn't necessarily that straightforward, because the crystal structure, all the atoms, they're actually vibrating, they're actually bouncing around, maybe not so uniform as I'm showing on screen, but they're bouncing around. So what happens is that some of those electrons are going to hit things and they're going to get bounced off. So it's like throwing a tennis ball at a wall. The electron is the tennis ball, it's going to get bounced off, it's going to go somewhere else. And so this is what resistivity is, basically, where we're not getting the flow of electrons, we're actually disrupting the flow of some of these electrons. And they vibrate very fast, but we can slow down this vibration by reducing the temperature of the materials. So the lower the temperature, the slower they're moving, which is fine. So it means that if we've got our electrons, it makes it just that little bit easier for them to run the gauntlet, to pass through. With superconductors, we have these other things happening as well. I think I've got my numbers wrong somehow. I'm not sure how. Anyway, let's not get into that. So around with superconductors, when we get to around 10 Kelvin or minus 200 degrees C, superconducting materials, not only do they this vibration slow down, but also it seems that the electrons go on like some dating app somewhere, and they go and get coupled up. So you know, I guess too many fish in the electron sea. So these electrons start forming couples, they start forming pairs. And these pairs, when they're traveling through the system, now you've got to hit them with a whole bunch of energy in order to divert them, because they're paired up. It takes a lot of energy to change the direction that they're flowing. So they pass through really easily. And so this only happens with superconducting materials. And this is great. It means that we have gone from having a resistance to having something that conducts really super. So it's a superconductor, which is, you know, kind of does what the name says. So they're conducting really, really well. And actually with some superconductors, well, all superconductors, we can have zero electrical resistance. There's also this extra little phenomenon that happens that because the materials, I'm saying atoms, but they're actually they're actually ions, because we've ripped off an electron, and so they're slightly positive charged and the electron is negatively charged. So as the first electron travels towards the ions, it actually pulls them towards it, and then because you've got this localized positive field, then the second electron is sort of pulled towards that, so it accelerates it. So there's a couple of different mechanisms that work in superconductors that allow us to pass electrons through the system, and it means that we can have very, very high currents for very thin materials, like I said, because we've not got the resistance, and it means that we don't have to that we're not melting our wires if we pass too high a current and things like that. Although I will say that there's a certain limit, we can only pass so much current, but you can use a very thin superconducting wire to pass much more current than a thicker non-superconducting wire. The only trade-off is you got to cool it down a fair amount. Like I say, maybe to a 20 or 10 Kelvin. However, we work with high temperature superconductors, so we only have to cool them down to around minus 200 degrees C, or around 70 Kelvin, because we're working at high temperatures, which it's all relative. It might not seem like much, but the advantage of that is we can use liquid nitrogen to cool down our materials, which is why we can do experiments on the desktop with superconductors that have been cooled down. And we did, there was a video earlier of a superconductor floating above a magnet. What's going on there? Well, superconductors also have these weird properties. If you introduce a magnet near the superconductor, then the magnetic field lines will just pass through like they would with other materials. However, once we cool the superconductor down, magnetic field can no longer pass through. It will no longer pass through, so it has to go around the superconductor. So what sometimes happens is if you've got the superconductor and you've cooled it down, then it looks like it sort of levitates above it, it floats. Now these are called type 1 superconductors, so these are our standard superconductors. But we can also have type 2 superconductors, so these can be sort of various compounds. And what we see here is that the same thing happens. If we cool a superconductor down without the presence of a magnet, the magnetic field lines are expelled. They'll no longer travel through, they have to travel around the material. But if we cool it down in the presence of a magnet, what we see is we actually pin these magnetic flux lines. They sort of travel through a particular area. So it's like water traveling through a pipe downhill. It'll funnel through. It's like a funneling thing. And so the magnetic field lines kind of want to stay where they are. They want to travel in that same direction. So if we move the magnet and we've cooled the superconductor down above the magnet, then what happens is that as we move the magnet, then the superconductor goes with it because it's pinned in place, it's locked in place above the superconductor. Obviously, if we pull it hard enough, we're able to pull it apart, but we can even turn the whole thing around and it will float and it will be held upside down. So it isn't floating and it isn't attracting, it's just locked in place relative to the magnet. The superconductor is locked in place relative. So if you design a magnetic track and you have a magnetic field line which is designed like an M shape, then and we cool down a superconductor and maybe keep it in some polystyrene to keep it cold, then we can have our superconductors floating above these magnetic tracks and moving around, and it's kind of fun to play around with, although it turns out that gluing 400 magnets next to each other is a little bit of work. So with that, that's the end of my talk. One thing that I'd like to just point out to people is that if you know about the STEM Village Conference, there's also an LGBT Seminar that happens. It's happened about 4 times now, 5 times in the UK. And we're actually going to be hosting that in Oxford in January, assuming we can all have a conference in January. And so it'd be really nice to see people there. We'd love to have you along and hear your science. With that, thank you very much.